Hello and welcome. By clicking on this video, you probably have some interest in chemistry and your health, or both. I don't know much about health, but for chemistry, I would strongly recommend the excellent YouTube channel Nile Red. Speaking of which, he posted this video a few years ago about the extraction of caffeine from coffee and mentioned the addition of sodium carbonate for a cleaner caffeine extract.
The sodium carbonate will react with a lot of different molecules in the coffee and make them more water soluble.
Right, so since I have put together this GC unit, I wanted to put this hypothesis to the test and verify how good sodium carbonate can actually remove extra chemical from the extraction process. So I proceeded to make coffee with and without carbonate, just like the video. However, unlike NIRED, I am not interested in yield since a few microliters will suffice to detect sub-nanogram of impurities. I've had a lot of problem with this old GC unit, but after fixing helium leaks, cleaning all the component, ordering and replacing the column, I've put it back on track. Also, one viewer suggested replacing the UV detector with a thermal conductivity detector, which I thought was a brilliant idea. But since I use dichloromethane for most of my extraction, chlorine would corrode and eventually destroy the filament in such a detector. So I had to scratch that idea. Anyway, here's the results from the normal coffee extraction without the carbonate, and compare this with the carbonate result here. And I think this little guy right here is actually the caffeine. Now, I don't want to venture an opinion too soon, but I would say it does work well, and the GC confirms it. What do you think, guys?
Totally confirmed.
It worked. Confirmed.
The reason why this happened is best explained in the original video.
I mentioned earlier that sodium carbonate is used to make certain things more soluble in water. This is useful because now that they're more soluble in water, they'll be less likely to be taken up by the DCM.
So obviously the extraction method has a huge impact on the result of the analysis, but one may also question the wavelengths chosen for detection. So next, I performed two extractions from tobacco leaves, one with water, followed by DCM, and the other simply by refluxing the tobacco in dichloromethane for 3 hours. Because of the low level of detection of the gas chromatograph, all the glassware I am using is thoroughly cleaned, and I don't always show this, but trust me, it's happening. If you watch my previous video on the gas chromatograph, I described the effect of temperature and how a lower temperature increased the separation of the peaks, but also increased the analysis time. But on this video, I wanted to explore the effect of the wavelengths chosen for detection and how it could be used to identify some potential molecule. So at constant temperature, here is the tobacco extract from water at 190 nanometers, 200 nanometers absorptions, and finally at 210 nanometers. This little guy down here, I believe it to be nicotine. Now, looking at the absorption intensity at various wavelengths, it could be in theory possible to identify the molecule responsible for those peaks here. The retention time gives us a clue of the boiling point and the size of the molecule responsible for these peaks. But again, without a standard, it's difficult to make a judgment call here. Now that we have established that, let's see what gets extracted directly from refluxing in dichloromethane after an hour, after 2 hours, and after 3 hours. Obviously here, most of everything gets extracted between 1 and 2 hours. I thought it was interesting and I wanted to share that. Now, we've all left a bottle of water in a car on a hot summer day, and we all know it isn't safe to drink because of the possibility of chemical leaching into the water. The chemical in question is BPA, or Bisphenol Acetone, from polycarbonate plastics. Most drinking water containers are BPA free nowadays, so I had to find one that is not safe for liquid storage and test this. And looking at the polycarbonate, it's not a stretch to see how BPA could be released. Of course, I had to make some to establish its retention time. BPA can be made easily by condensing phenol and acetone in the presence of an acid catalyst. After extraction in dichloromethane, I thought I could get the peak I was looking for, but unfortunately, biphenols are notoriously unstable and difficult to observe with a gas chromatograph. But without a HPLC, I tried anyway. So I first filled the container with deionized water, and to increase the concentration and maximize my chances, I microwaved it several times for several minutes before putting it out in the sun, hoping the ultraviolet will break some of the OH bonds and free some BPA into the water. Now, I think my results are somewhat inconclusive. I may have had some contaminated solvent at some point, but you can let me know what you think in the comment below. Here is a 30-minute blank at 200 nanometers. Here is a phenol on its own, and this is the BPA I've made. Acetone is mostly gone, but the excess phenol is very much here. It's worth noting that some BPA can decay back into phenol, increasing the already very high concentration. I've used more acetone on the second batch, and you can see it's still right there next to dichloromethane. Still a lot of phenol, and notice this tiny peak right there, which I believe is BPA, and I'm not sure what else it could be. So here's the polycarbonate box water sample, and again we can see that peak showing up. This peak came back every time I've injected any potential BPA candidate. However, changing the wavelength only decreased its size, when it should have been rising between 230 to 270 nanometers. And to be honest, I'm not quite sure what to make of this result. So, this is probably not your first YouTube video, and you know what to do. Thumbs up if you like it, subscribe if you want, Patreon, bell, share. I hope to see you again on the next one, and thank you for watching. Damn it!